Hi guys. Well, this is going to be a quick video to help summarize as well as clarify a few core paper 1 AS level computer science 9618 theory fundamental components. So this is going to be a study guide of sorts where we'll be discussing theory content, like I said, of very important essential parts of the paper 1 syllabus, plus looking at some past paper questions as well. Let's jump right in. So the first topic I'll be going over is about laser printers and magnetic hard disks. These are two very important devices, peripherals that we can connect to a computer in the case of laser printers, to print out things, to produce hard copies of digital documents. And in the case of magnetic hard disks, serve as a secondary storage device. But for all purposes in this syllabus, we consider them as peripherals. To start off with laser printers, how do laser printers work? I'm going to describe to you guys how laser printers work in 6 main steps. We'll first look at the first 3 steps. A laser printer is essentially made up of a drum that rotates inside the printer, right? And this drum, on initial rotation, gets charged using what we like to call a uniform high negative electrostatic charge, right? So that's the very first thing that happens. The drum that's rotating receives a uniform high negative electrostatic charge, right? And that's these, you know, uh, cyan blue colored circles with negatives inside them representing, right? So that's the uniform electrostatic charge that's distributed across the entire drum. And then what we do is we perform the second step, which is exposure, where we shine a laser beam into parts of this drum, which scans the drum left to right. And essentially, everywhere that the laser strikes the drum, the charge gets neutralized. And the idea is that what then this allows us to do is it allows us, based on what image we're trying to print, neutralize certain areas of the drum and not neutralize other areas, essentially creating what we like to call an invisible image, which we can then stick toner to sort of print out the image that we need. So essentially, we discharge the areas of the drum where we want the image to appear. So this creates like this invisible latent image that is currently composed of charges, but once we add toner, the areas that don't have the negative charge will have toner stuck to it, which is what then appears on the paper. So what then happens is exactly what I was talking about. We can then apply negatively charged toner particles, right, to the drum. So you have this powdered ink that is applied to the drum, which you will see in more detail on the next page. And since the toner is also negatively charged, they are repelled from the areas of the drum that are also negatively charged. But they stick to the areas of the drum that are less negative, or in other words, where the laser has neutralized the charge. So the particles are attracted to the discharged regions of the drum, sticking to the areas that don't have negative charge. And then to talk about the last few steps, here you go, you can see the toner being deposited onto the positively charged areas of the uh, drum. Again, this can happen on in the opposite way as well. You can have negatively charged toner that are attracted to the drum, or positively charged toner attracted to the drum. Whichever direction of charge doesn't really matter, but the former is what's most commonly used. And then what we can do is we can take a paper that receives a positive charge, which arrives from a different roller called the transfer roller. And then this positively charged paper attracts those negatively charged toner particles. So in essence, you initially have a drum that's negatively charged. We use a laser to kick off the charges in the places where we want the image to appear. We then go and apply negatively charged toner particles onto that drum, which then sticks to the areas that don't have the charges. So in other words, the areas that the laser discharged. And then you can imagine that the drum has overall negative particles, be it the electrostatic charge that was already in the drum, or now the negatively charged toner particles. But then once you pass through that drum a positively charged paper, and these are all electrostatic charges, by the way. The positively charged paper attracts a negatively charged toner because positive and negative attracts, pulling toner off of the drum onto the paper. And then now those powdered particles are on the paper very nicely. What we can then do is we can permanently bond the two together by passing it through a bunch of rollers which permanently heat the toner onto the paper, creating a bond, right? That's the fusing stage. And then finally, we clean the sort of drum so that we are ready for the next time we want to print a document. So a blade removes the residual toner from the drum, and the drum is recharged, ready for the next page. Right, cool. So that's how a laser printer works, guys. Feel free to go back, revise if you guys have any doubts, or leave any questions under the comments. Now we're going to look at a magnetic hard disk. A magnetic hard disk also I'll explain to you guys in 6 steps. A magnetic hard disk is composed of these components that you see on the right-hand side. There is a platter, which is this ferric material component. In other words, it's made up of a magnetic material that spins at a very high speed. So one of the main components of a hard disk is that you have these platters that spin, and they're made up of ferromagnetic material, and they spin at around 54 to 72,000 RPM. So they're quite fast. And this platter is where the data is contained in the form of negatively or positively charged particles. So in order to actually find out where data is stored on this platter, or read data from this platter, or to write data to this platter, whatever, you need to seek. What does it mean to seek, guys? Seek means to move this so-called actuator arm, which is an arm that can move left and right along the platter radially to locate the correct track in which our data is stored. I'll explain to you what tracks are on the next page, on the next slide, but a track can be imagined as a concentric ring around this platter, right? So the actuator moves like a DJ scratching a disc on top of this platter. And one cool, very interesting thing about this platter, or actually this actuator arm, or this read-write head, is that this head flies on top of the platter, nanometers above the platter on a thin air cushion, which means that it never ever contacts the surface during normal operation, right? So you can imagine, a kind of system where there's this cushion of air in between the actuator arm or the read-write head and the platter, which essentially separates the two with nanometers of difference. And then the idea is, this is what I was explaining to you guys earlier. What we meant as a track is these concentric circles around a disk, right? Now, these platters rotate while the read-write head moves, which together allows the read-write head to locate a specific sector, which is the intersection between a portion of the hard disk drive platter and a track. This portion is also referred to as a sector. This is the sector that you guys might be familiar with from maths class, where circles can be divided into sectors. So that sector, like the pizza slice looking component intersecting with the track, also known as a cylinder, forms another block, which we like to call a sector as well, which is where the actual data is stored. So the read-write head can locate this sector, right? And that's called rotational latency. And then you can apply magnetic fields to induce electrical currents in the head of the coil based off of what's on the disk, right? That's usually what happens when you read. So magnetic field variations on the read-write head can be then decoded into binary data to read what's on each of these sectors. And when you want to write data, you can pass a current through the coil to generate a magnetic field, which then changes what's on this sector. The magnetic particles spin can be altered to either spin up or spin down, in other words, to represent zeros or ones. When I say spin, it's similar to North Pole, South Pole magnets, where you can change the polarity of the particles that are stored in the sectors, which in turn represents zeros or ones. All right, so that's how magnetic hard disk works. Now we'll look at ROM, PROM, EPROM, and EEPROM. Now this is fairly simple. You guys all know what ROM is. It's essentially read-only memory that is used to store firmware and the BIOS. Now, ROM was manufactured, in the 1970s, 1960s, during the early days of computing, as a permanent store of data, which means that the stuff that you put into ROM is fixed permanently during manufacture. It is non-volatile as it is today. And back then, as it is today, it was used to store firmware that must never change. But this is a problem because if there was an error during the manufacture process or during the data loading process, you have to discard the entire chip, which is a waste of money as well as a waste of resources. And if we had to update the BIOS later, we could never do that because it was written permanently into the ROM. So then came a different kind of ROM called PROM, programmable read-only memory, where it was shipped blank to the consumer, and the consumer could write it exactly once using a programmable read-only memory programmer device. And this is an example of one of the very first PROM chips, right, during the 1970s. Once programmed, it behaves just like the old one, where once you program it once, you can never change it, which means mistakes are permanent. However, why PROM was better than ROM, of course, is that it was programmable at least once, which means that the user could program it however he likes. So it allows post-manufacture customization of the same chip for different products. Cool. Now we go on into what we use today, starting off with EEPROM, which is not what we use today, but we are closer to today, where EEPROM is erasable, but not using the standard electronic erasure. It's erasable using UV light. So the next kind of PROM chip that came into light was EEPROM chips, where you can apply a strong UV light through a quartz window. So these EEPROM chips that you can see on the right-hand side had this opening that allowed UV light to pass through. But in order to do this, you need to physically remove the EEPROM chip from the circuit board and then apply the light. Yeah. But once it's applied, the chip erases itself completely, which then we can reprogram afterwards, right? So it's useful for development and prototyping use cases. Then after that, we arrive at the ROM type that we use today, where we don't have to do this shining in the light kind of system, where we have to remove the ROM chip and then take it out into the sun. We don't have to do that. We can, erase and reprogram everything on this ROM chip programmatically, and electrically. So EEPROM stands for electronically erasable programmable read-only memory, whereas the single EEPROM stands for erasable programmable read-only memory. So the first one is only erasable through UV light. The second one is erasable through electrical signals. So we can erase and program these EEPROM chips electrically byte by byte without removing it from the circuit. And this is what we use in SSDs, USBs, and modern BIOS chips, right? It enables anyone to remotely update their firmware without having to, break an arm and a leg and remove the chip and shine UV light at it. But the limitation with this kind of thing is that it's more expensive to produce, as well as there's a finite number of write and erase cycles you can do to a EEPROM chip. So it's not as volatile as you would like. It's not it's not as volatile as you would like, or it's not as read-write friendly as you would like. It's still limited in the number of read-write cycles or erase-write cycles you can make. So just to go over some key differences between EEPROM and EEPROM. The first difference is the erasure method, where EEPROM uses electrical signals, whereas EEPROM uses UV light. Then, in terms of erasure, EEPROM must be removed from the circuit to erase it, where you to shine UV light at it, whereas EEPROM can be erased in the circuit itself through electricity. Next up, erasure granularity, that is, EEPROM can be erased individually, byte by byte, whereas EEPROM can only be erased at once. Everything has to be deleted altogether. Then the practical advantage is that EEPROM allows for firmware updates after the ROM chip has been sold to consumers without having to replace the hardware. So here are some past paper questions which I'd like you guys to go through. Please feel free to pause the video and go through the answers and the questions. Just make sure that you internalize the kind of questions you get. Right. So now we move on into topic 3, which is monitoring and control systems. Now, what is the difference between monitoring and control? Monitoring systems are systems that have sensors to measure and record data. And then what they do is they may alert the user about some kind of um, issue that occurred during that process, some anomaly of sorts. But it does not take any automated action on the environment itself. It may do alerts, it may do logging, it may not do any action by itself. So that's monitoring systems, where a sensor passes information to a processor, and if there are any anomalies that were detected, it would alert the user. Now we get to control systems. Control systems are slightly different because they can do exactly what monitoring systems do, pass inputs from sensors into processors, which then activates actuators, which are physical components that can actually change the physical environment and then subsequently update the next set of inputs to the sensor because the environment has now updated, right? Which leads to this concept called feedback, where the output of an actuator feeds back to input to the next sensor reading, which continuously creates this correction loop, right? So it's kind of like homeostasis of the human body, where the human body maintains, blood pH levels and things like that, um, as well as this is the case with animals. So if you guys are familiar with biology, it's kind of a similar system, but the idea is that when you make changes to the environment updates itself, hence changing the next set of sensor readings. So there's this continuous feedback loop that happens with monitoring, that happens with control. Sorry. So that's the idea. And the key difference you need to keep in mind, and the key thing that they ask you that they try to get you guys to remember at the exam is that if a system can act automatically, that's a control system. Whereas if a system can only record or alert the user, that's a monitoring system. Cool. All right. Now we'll look at a few types of sensors that you need to know for the exam. First, we have a temperature sensor, which, as you guys know, is a very standard sensor that measures thermal energy, which is used to measure how hot or cold the surrounding environment is, right? It measures thermal energy and outputs an analog signal proportional to the temperature in the ambient environment. And this is used for greenhouse automations, industrial cooling, etc., etc. So any situation where you need to measure temperature, use a temperature sensor. Then we have pressure sensor. It detects force per unit area. For those of you that do physics, you guys know that pressure is equal to force over area, right? So that's exactly what it measures. And it's used to detect vehicle weights. It's used to check whether intruders are trying to come into your house by introducing pressure sensors under mats. If you guys have seen cars having alarms that go off inside the car when you don't buckle your seat belt, is because there are sensors that detect whether a person is sitting down on that seat but not wearing the seat belt. So pressure sensors could be used there as well. And then for measuring or monitoring tire pressure, you can use pressure sensors as well. So I forgot to link these things to the diagrams on the right. So these are on the right-hand side, you can see some images of these sensors. So this is a temperature sensor. This is a pressure sensor. Now we look at infrared sensors. Infrared sensors detect heat emitted through IR waves. So if you guys are, again, coming from a physics background, there are three ways that heat can conduct: conduction, convection, and radiation. So if heat is conducted through radiation, you can use IR sensors to detect it. But also, you can use it to detect reflected IR signals, which is used in TV remotes. It's used in controllers, things like that. So infrared is used therefore for motion detection and also proximity sensing. And then sound sensors, which, by the way, sorry, I forgot to link. Here is an example or a picture of an infrared sensor. Then moving on to sound sensors. Sound sensors detect audio pressure waves. So these are very similar to microphones, if not the same as microphones in most situations. There's no image on the right-hand side for a sound sensor, but it's essentially a sensor that's used to detect sound. This is more or less a microphone, but it could be dedicated sound devices, sound input devices as well. But regardless, they're used for voice-activated systems and monitoring noise in different scenarios. So keep these things in mind, use them in your answers when you have to explain the use cases of sensors in specific monitoring and control software applications. Now, to give you guys a quick recap of actuators. Actuators are output devices that convert electrical signals from the processor into a physical action, right? These are what's used in a control loop to sort of perform changes on the environment. Examples of actuators are motors, heaters, valves, warning signs, alarms, pumps. So anything that can change the external environment. So here on the right-hand side, you can see the control loop diagram where the sensor passes information to a processor, which then takes action by sending signals to the actuator, which then updates the environment. And there are two components in between the sensor processor and processor actuator. The sensor sends signals to the processor via an analog to digital converter, right? And the processor sends its signals to the actuator via a digital to analog converter. And the reason why this is important is because a sensor measures data using analog signals and sends it to the processor uh, in that same form, but the processor is only able to understand digital signals. So we need to have an ADC, analog to digital converter, to convert analog signals from the sensor into digital signals that the processor can read. And the same thing happens to be done the opposite way through a digital to analog converter, where the processor can output digital signals, which the actuator is then supposed to um, receive in the form of analog signals, right? And feedback is super important in this control loop, and that's why it's called a loop and not just a sequence, because without feedback, a control system is unable to verify whether the action achieved the desired result. So for example, imagine there's a huge vat that's mixing some ingredients together to let's say manufacture yogurt. But imagine this vat has pH sensors to detect the acidity of the yogurt, and it adds some acidic or alkaline liquid, some acid or alkali to the yogurt mixture to regulate its pH, right? Now, imagine the system detects that there is too much acidity in the yogurt. It might reduce it by adding some alkali. But then if there's no way of measuring whether that change resulted in a pH increase, that is to make it more alkali, less acidic, what will end up happening is that it'll keep adding more and more alkali until it becomes, I don't know, like a terrible alkali poison that would kill the people that eat the yogurt. So in order to prevent this loop from going on forever and end up creating some concussion of ingredients in the case of a yogurt manufacturing vat, you would have a control loop that is able to then update the sensors the next time as a result of updating the environment, which is then able to regulate the addition of alkali or the addition of acid, whatever, to keep the pH under control. So feedback enables continuous comparison of actual state with the desired state, which allows us to automatically correct our actions. So here are some past paper questions which I'd like you guys to look at to see how sensors, actuators, monitoring and control systems are used and how examples or answers to those questions are written at the exam. But yeah, feel free to pause the video to go through this. And right. Now we'll look at von Neumann model and CPU registers. The von Neumann model uses something called the stored program concept, which is where instructions and data are stored together in the same memory in binary form. Keep this in mind. Instructions and data are stored together in the same memory in binary form. That's the stored program concept. And in the von Neumann model, programs can be loaded, modified, and replaced without any hardware changes. Cool. And then in the von Neumann model, it also follows the fetch, decode, execute cycle where CPU is able to fetch instructions from the RAM step by step, instruction by instruction sequentially. And this is actually controlled by the program counter, as you will see in the next slides, where after the instruction is fetched, it decodes that instruction into opcode and operand and executes them one by one. Like I said, this is the fetch, decode, execute cycle or the fetch, execute cycle for short. And the major components of the von Neumann model is the CPU, which consists of the ALU, CU, and registers. Control unit is the abbreviation for, control unit is what CU stands for. Then there is main memory, which is also referred to as immediate access store. And then there are three buses that connect all of these together: system bus, control bus, address bus, and data bus. So here you can see a simplified diagram of the von Neumann architecture. Feel free to take a look at it. Feel free to take screenshots, whatever. Make sure that you understand this diagram and the components involved. Now to look at the three buses, the von Neumann architecture is first made up of, consists of an address bus, right? Which is the unidirectional bus that carries data from CPU to memory or input-output components. So if you look at the address bus, there's an arrow to the address bus from the CPU, but then only from the address bus to the memory and I/O, not the other way around. So keep that in mind. Address bus is unidirectional. It carries memory addresses from the CPU to the places where data is to be read or written from. So it's used to identify where data is read or written. Then we have data buses, which are bidirectional. As you can see, data bus has double-headed arrows connecting to each of the three components, which carries data or instructions from CPU, memory, and I/O devices. And finally, you have control buses, which are again bidirectional, which control signals that control the rest of the components. I'm sorry, I said control signals. They send and receive signals which control the rest of the computer, right? So keep in mind, control bus is bidirectional because the CPU can send instructions or control signals to the rest of the components, but the rest of the components can also send instructions to the CPU, for example, in the case of interrupts, right? So control buses are bidirectional, like I said, and they carry control signals that indicate when to read and write, carry clock signals, carry interrupt signals, carry bus requests or grants, whatever, right? And together, control address data bus is referred to as the system bus. And there was a question in the exam where there was this question where you were supposed to answer what kind of signals are sent along a control bus. So please keep in mind, control buses send read-write signals, clock signals, interrupt signals, bus request grant signals. So keep these things in mind because they might ask you what control buses send and receive. So these are some answers you could write. And now to quickly discuss about some of the registers that we have, which I'm sure you guys already know. We have a program counter, which is a register that's used to hold the memory address of the next instruction to be fetched. And then it also automatically increments each fetch. Then we have a memory address register that holds the address of the memory location currently being read from or written to. And then we have the memory data register, which holds data just read from or about to be written to memory. And it acts as a buffer between the CPU and the RAM. Now to move on to the remaining special purpose registers, we have a current instruction register, which holds the current instruction that is currently being decoded and executed. Then we have the accumulator. This is a general purpose register. So although I put this under special purpose register, keep this in mind. Small error in the slide. This is a general purpose register. Very, very important. Accumulator is general purpose. It is not special purpose. It is general purpose because it can hold any kind of data. It's kind of like the dustbin of registers where you can put any kind of data into it to hold results of ALU arithmetic and logic operations, right? Then we'll look at the index register, which is used to hold offset values used in indexed addressing, which is used for array traversals in memory. And then we have status registers, which is used to hold bits of flags that reflect the outcome of the last ALU operation. So imagine after the previous ALU operation, imagine there was an addition operation and the result led to an overflow error. Then the status register would hold a flag corresponding to an overflow error. Likewise, if there are errors corresponding to ALU operations, those error flags would be stored in the status register. All right, take a look at these questions that are some from past papers that test your knowledge on the things that we discussed, so registers as well as the buses, and there might also be more questions from previous papers. By the way, just to give you guys some context, these questions are only extracted from the 2024 and 2023 and 2022 past papers, not before that. So you might find more questions on this from older past papers. But yeah, that's that. Take a pause, go through the questions. And yeah, let's continue. Next up, what are some factors that affect CPU performance? Well, the first factor that affects CPU performance is clock speed, which is the number of fetch decode execute cycles per second. When you write answers that discuss the impact of clock speed on instruction execution, please say that higher clock speed equals more instructions processed per unit time. Very important. Please address that this is per unit time. Don't just say higher clock speed is equal to more instructions. Please say that it's more instructions per unit time, per second, per minute, whatever, right? Upgrading to a faster processor would directly increase throughput, not only because that would result in a higher clock speed sometimes, but because architectural improvements in the processor will also mean that more data can pass through the CPU at a unit time. So upgrading to a faster processor would increase CPU performance and computer performance overall. Then another factor that improves computer performance is the core count, which is mini processors inside a CPU, right? Each core is able to process data independently of each other. So if you have multiple cores in your CPU, it's able to perform parallel processing. So each core is able to perform its own fetch, decode, execute cycle, which means that multiple cores enable true parallel execution, true simultaneous execution of multiple threads of work, which means that it reduces the total execution time for multi-threaded workflows or workloads. So if you have applications that are able to execute on multiple threads, it's able to do multi-thread execution or parallel processing for the just to keep it super simple. Then the higher core count will directly influence how fast it can execute. Now, a few more features that influence computer performance: cache memory. Cache memory is a very small but fast memory on or near the CPU that is used to store frequently accessed instructions and data. So it acts as a form of meta memory or a form of intermediate feeder memory in between the CPU's registers and the random access memory, right? A faster or larger cache reduces the chances of cache misses, which is where the CPU tries to find something in the cache, but it's not there, so it has to go and find it in the RAM. It reduces those occurrences, which reduces the need to access the slower RAM, which improves execution speed. So here is a diagram that showcases the CPU caches. Usually cache is divided into three main levels: L1, L2, which are often in the CPU, and L3, which could be out of the CPU, but sometimes in the CPU as well, but it's a shared cache. And this, as you can see, is all between the registers of the CPU and the RAM. And then finally, the other factor that influences computer performance is the bus width. Bus width tells us how many bits are transferred between the memory and the CPU per clock cycle. A wider bus, for example, 64-bit bus versus 32-bit bus, allows for transferring more data and more addresses per cycle, which allows us to either increase the number of instructions that we can execute, or in other words, increase the quantity of data we can transmit per second, which reduce the number of transfers needed for larger operations. So for example, if you had a 64-bit value to transfer along a bus that was 32 bits, you have to segment it in two and then send it in two passes. So if you have a 64-bit value to send across a 32-bit bus, you need to send 32 bits first and the remaining 32 bits later. Whereas if you had one big 64-bit bus, you could send that 64-bit value once through the bus and call it a day. So that's the idea, right? When you have large operations to do, and if you have wider buses to accompany those operations, the number of transfers needed would be lower, which result in a direct improvement in performance. So here are some past paper questions which I'd like you guys to check, which essentially refer to what we just went through. And right, now we'll look at some utility programs, disk formatters and disk defragmenters to be specific. Disk formatter is a utility software that prepares a storage medium by use for a specific operating system. So it's sort of a preparatory software that allows cleaning a disk to prepare using it for by your operating system. So a utility software that creates and prepares a storage medium. And a disk formatter is able to create something called a file system structure, which composes of these things called a partition table, root directory, and a file allocation table, the specifics of which you don't have to remember. So you don't have to remember these terms for the syllabus. So I'll just mark it as not in syllabus. But keep in mind that the utility software disk formatter is able to create a file system structure, which is what then allows us to store files in that new disk. It could be a USB, it could be an SSD, whatever. Once it's formatted, the file system structure would get created. There are two different kinds of format that we work on. There's a quick format, which just overwrites the file system metadata, which means that the actual data sectors in that disk is left intact. So that's quick formatting. And then we have full formatting, where you write zeros or random data across to every sector, which securely erases all of the previous content. Yeah. And then once a disk formatter is used, after formatting, the disk appears completely blank to the operating system, regardless of the prior content. So that's the end goal of disk formatting, to completely clear the drive, either through quick formatting or full formatting, so that it appears blank to the operating system, which is then what you can do to, write data to that drive and work with that drive afterwards. Now to look at defragmentation software. This is mainly relevant to hard disk drives, where when files are created, modified, and deleted over time, the blocks of data corresponding to those files, which are small pieces of data that form the full file, right? That's what we refer to as blocks. Those blocks become scattered across sectors of the hard disk drive. So you can see this diagram here, where a file has been distributed across multiple sectors, whereas normally a file should be next to each other along one track, along a set of subsequent or sequential sectors. So when this happens over a bunch of read and writes, this is referred to as fragmentation. So a file gets fragmented over time. As a result, this requires the read-write head to move to many locations quickly, which increases the seek time, which is the time it requires to find a sector, which lowers the read-write speeds. Defragmentation software is able to reorganize this data so that files that are distributed across sectors are now placed sequentially. So a file occupies continuous sectors, which then reduce seek time. So in one single sweep of the read-write head, you can find all the file's sectors. One quick thing to note, though, is that defragmentation is unnecessary and harmful to do on SSDs because SSDs don't have any moving parts, and the seek time is irrelevant for SSDs because, again, there's no read-write head that needs a certain latency to access things. It's done electrically, right? Topic 6, we'll now look at IDEs. What are some features of integrated development environments? The first feature is that IDEs have these things called context-sensitive prompts, where as you type code into an IDE, it is able to suggest valid completions as the programmer types, which allows us to reduce syntax errors and speeds up coding. So this is kind of like autocomplete, but not in the form that it completes your code for you, but it suggests what the next code you should type is, or what the method name you should type is, or what the variables you should type is. This is not AI. This is just a simple context-aware prompt that tells you, based on the code you're typing, what could be the suggested next word. Then IDEs are also able to perform dynamic system syntax checks, which is where the IDE is able to analyze the code in real time and highlight errors before the program is compiled or run. Then IDEs are able to perform pretty printing, which is where it can automatically format code with consistent indentation. It also supports color coding, which helps us read the code more clearly. And then finally, if you have large code blocks, especially functions, it allows us to expand and collapse these code blocks so it can help us easily navigate through a larger file. So here is a screenshot from my Visual Studio Code where I'm showing you guys a JavaScript code snippet. Here, if I were to go through the features that we discussed before in VS Code, which is an IDE, you can see pretty printing in action. You can see beautiful indentation, highlighting, colors, all of that. So that is pretty printing. And then you can also see collapsing in action. So you can see how the format date function has been collapsed. Using that arrow, I can collapse and hide blocks of code. What else? Can you see how there is this prompt on top that tells me what this function's parameter set is and what its return type is? It's saying that the parameter that this function takes in is this parameter called ISO. That could be any type, but its return must be a string. This is kind of similar to a context-aware prompt. Context-aware prompts could be way more contextual. Context-aware prompts can sometimes contain a lot more detail, but this is a very preliminary form of context-aware prompts, where it just tells you what your functions in parameter and return types are, which is helpful because if you're doing integration testing or if you're trying to figure out what this function does at a glance, you can quickly hover over that block of code. That's the function name, and it'll tell you what the key characteristics of the function is, right? So that's that. Then last but not least, dynamic syntax checks is not visible through this screenshot because dynamic syntax checks happens when you run your code or while you type your code for that matter, where the IDE is able to analyze the code in real time using these things called language servers and highlight any errors as you type your code. So yeah, that's that. Now, IDEs also have features for debugging, where IDEs are able to provide you with breakpoints where when you want to debug your program, you can mark a line where execution pauses in that line. So as you execute a program through a debugger, it will stop executing in that line. So in this code block here, this is the Google's own DevTools IDE that you see. Here, some person has written a for loop and he's debugging that for loop, and he's added a breakpoint on line number 3, which is where, as he's debugging, it stops in that line. It tells you what the value of X is, what the value of I is, so you can actually inspect what's going on at that time. And this sort of window here that tells you what's happening in the program, what the variables values are, is called the report watch window, where it can display the current values of specified variables in real time throughout execution. So that's exactly what you saw just now. But yeah, speaking of breakpoints, it's able to sort of pause the program as you debug, so the programmer can inspect the state of all variables at that exact point in time. And then in order to be able to execute this line by line manually, you have a feature called single stepping, which is where after you pause at a breakpoint, you can advance one line at a time, observing how each statement changes the variable's values. So this is the button on this screenshot that allows us to single step. This actually helps us go into a function further rather than step over a function. But imagine you have a loop, imagine you have a function, it's able to go into that function and step through the program line by line. So yeah, that's single stepping in action. And then in practice, breakpoints help us isolate where the bug starts, right? It helps us figure out where the bug is sort of happening. But then single stepping is what then helps us step through that code block from the breakpoint to identify the exact line that's causing the bug. So here are some past paper questions for you guys to check out more details about the kind of questions you get for IDEs. So here it's a question about describing the different IDE features. Cool. Here's another question for you guys to check out, which is where you are supposed to describe for 4 marks what the debugging features of a typical IDE do. And yeah, that completes the walkthrough for this video. Check out my other videos for further revision on other paper 1 topics. But if you have any questions, please let me know, and good luck for your exams. Bye-bye.